Howdy y'all, I want to start this video on entropy, and we have a guest speaker. We are super lucky to have this guy. He is a master on this kind of topic. So let me go get him. Alright, here he is. Hey, it's Max. Look, here's my son, and he is the master of entropy, the best person that really understands it. So let me show you what I mean, because entropy is really the unit of disorder, the disorder of the whole universe. Let me show you an example. So if I move my camera around so I can see it right on the desk, and I'm looking at one of his toys. Oh, let me scoot that up. At his toys, it's got a 5, 4, 3, and it goes on. So there is only one way that these could be arranged. The smallest one has 1, and there are 2, and there are 3, 4, 5. Okay, they can't be they can't be in reverse order. They can only be just in this order. So if I set the system all together and let the master of entropy go to work, what do you think happens? It gets destroyed. That's right. Little kids are the best models of entropy, because they're just you always find things in a different arrangement. Okay, that's enough of that. Let's start our chapter 17 notes on thermodynamics. The definition of entropy is with the letter S. That's how we write the symbol, as the symbol S. A measure of randomness or disorder, and it's an increase in the number of microstates. Microstates is where the particles could be, so that's what a microstate is. It's associated with the probability, or the probability that they could be arranged. So there's more ways for something to be disorganized than organized, kind of like that arrangement of the toys that I just showed you. The spontaneous process is something that's thermodynamically favored, that occurs without outside information, but it could be fast or it could be slow. This is what entropy has to do with chemistry. Entropy is more of a physics thing, but it really has a lot to do with the chemistry as well, because we're looking at if the reaction is thermodynamically favored or spontaneous. This is a great little picture also to illustrate it, of how entropy could be, because it's disordered. It's nice to see how at least in a picture, and but also from the example. So it's basically everything is spread out. It's kind of like my desk. I always try to clean my desk, but then it just keeps getting messed up all over again. This slide is an explanation on whether entropy will increase or decrease. What we want to focus on first is on if it's increasing. So an entropy increase is going from a solid to a liquid to a gas. That's because the molecules are getting more disorganized. They're very organized when they're a solid because they're all locked together, and then they're a little less disorganized when they're a liquid because they're kind of moving around a little bit, and then they're even more disorganized as a gas because they're just flying around all over the place. The entropy increases when the solutions are formed, and the entropy usually increases in a reaction when more atoms or molecules are formed. When more atoms or molecules are formed, what I mean is something like if H2O were to turn into H2 and or hydrogen and oxygen. Hey, it's an unbalanced equation, but that's okay. It is now more molecules are being formed here, so that would be entropy increasing right there. That would be entropy increasing. And entropy increases with increasing temperature, because that makes sense. As the temperature increases, the molecules move faster, so they're more disorganized. Here's it shown in a picture right here. If we had an ice cube that was a solid, it would be very ordered, and then as it went to a liquid, it's more spread out over time. So this is a thermodynamically favored reaction where it moves from a solid to a liquid. You've seen ice melt before. This is the minimum entropy here, which has the maximum amount of order, and then a lower order here. You could even go farther over here and make it steam, where the entropy would be increasing again, just like you saw here. So remember that these arrows right here, the distance of the arrow represents the speed or the magnitude of this vector. So that's why the arrows are longer with the gas, because the molecules are moving faster. So let's think about physics for a second, and let's think about the second law of thermodynamics. Now, we're going to think about entropy in the very big picture. Okay, think big picture. Big picture. Big picture. Here's a picture right there. Yay, you see a little smiley face. There's the big picture. All right. In any spontaneous reaction, there's always an increase in the entropy in the universe. So the entropy is always increasing. So entropy is always moving up, and it's always spreading out. And that actually will make sense, because if an Eskimo sits in an igloo and he's making a lot of warmth, he has a lot of heat. If that campfire goes out or something goes out, he will eventually lose that heat to the atmosphere. The heat will dissipate out to the outside universe, and it will keep on moving out farther and farther. Molecules are spreading out even more and more. The universe is constantly expanding. Now, the reason why we're studying entropy is so we can really study the free energy, because the free energy, or the Gibbs free energy here, that's Gibbs, Gibbs, Gibbs free energy, is the free energy change in a measure of the spontaneity, or the thermodynamic favorability. That's the key word. That's the word they like to use now. They used to use spontaneous, but now they like to say thermodynamically favored. I guess because they wanted more syllables. But it's the maximum work available from the system. So what that means is that we have enthalpy here. Enthalpy is RH, okay? And the enthalpy and the entropy and entropy will be related somehow as a function with temperature involved to form the Gibbs free energy. So the Gibbs free energy can be defined by a spontaneous, thermodynamically favored reaction carried out at a constant temperature and pressure has a negative delta G. So and you'll notice here that the temperature and the pressure will play an effect here. So you need to, the AP test will usually tell you that pressures remain constant, just to try to keep things a little simple so you can understand it. But if it is spontaneous, then it has a negative delta G. Okay. I know it sounds a little weird, but if it's spontaneous, or if the reaction will move on its own, it will have a negative delta G. That's what a spontaneous reaction means. It will move on its own, or it will start on its own. move on its own. So on its own. So think about like, um, what if if I had a ball that was going to roll down the hill, it will roll down the hill on its own. That is a spontaneous reaction. The ball will not spontaneously roll back up the hill. So that's what I mean by spontaneous. So based on the previous equation that I had there, if you can just kind of figure that out if you know that if the delta H is positive, so if this one is positive, and the delta S is positive, um, and delta G is 0. Yeah, okay. That's when ice melts, delta H is positive, and delta S is positive at delta G equals 0 at 0 degrees Celsius. So there's a lot of conditions to be there, and you need to really try to understand the equation before. So if delta S is positive, here are the conditions right here. If delta S is positive and delta H is negative, it is spontaneous at all temperatures. If delta S is positive here and delta H is positive, it's spontaneous at high temperatures. So if I rewrite the equation here, delta G equals delta H minus T delta S, I can see that if this one is positive and this one is negative, then delta G will always be negative. Okay, so think of it in terms like that. If delta S is positive, that will make this term a negative right here. And then if delta H was positive, it might be spontaneous or might not. So that's why these two in the middle are kind of depend on the temperature. So delta S is negative, delta H is negative. It depends on the temperature. If delta S is negative and delta H is positive, then it is definitely going to be non-spontaneous, because this term right here will be a positive term, and then this one will be a positive term. So you know that delta H will definitely be positive. That is a lot of information to absorb, but the whole lesson can really be summed up in this slide, where you're trying to understand that delta G equals delta H minus T delta S. That is what I want you all to understand, and try to understand that under certain conditions, under these conditions, you can use this equation to try to figure it out. Try to see if this one was negative or this one was negative, and see if you can understand. So now, remember that if delta G is negative, it is spontaneous. Spontaneous. If delta G is positive, it is non-spontaneous. Non-spontaneous. Okay? Spontaneous. And I'll just write spon right there. Okay? Thank you all very much.